Hi, I'm Daryl Nail with NASA's Communications, and welcome to Ascent Abort 2 pre-test briefing. This is going to be a full stress test of the Orion launch abort system, and it's critical to find out exactly how well it's going to work. And to talk about this, we have a special panel of guests that I'm going to introduce you in just a little bit. This test is critical because it's going to come before the Artemis 2 mission, which is going to be the mission that puts the first woman and the next man on the surface of the moon. And so joining me now is Jenny Devolites. She is the AA2 Crew Module Manager and Test Conductor. To her left, Mark Kirsich, Orion Program Manager. And to his left, NASA astronaut Randy Bresnik. All right, we're going to take your questions in just a moment, but we're going to get started with individual statements from you guys. And we'll start with you, Jenny. You've got some slides and a video to kind of show us exactly how this all works. We were talking a few days ago. You've been working for 3.5 years up till this point. Now we're just a short time away. How are you feeling? How is your team? What's the mood?
Incredibly excited. You know, it's such an honor to be part of this activity and to have this opportunity. Really had an amazing group of people. So happy we could help benefit the Orion program with this flight test, but really lucky. All of us just excited about tomorrow.
Well, let's take a look at the slide here and kind of explain how this setup works.
Sure thing. So tell you a little bit about the flight test vehicle that you see up on the screen. So on the right-hand side, you see the full-up flight test vehicle, but I want to talk about the 4 major parts of it that we're flying. So in the middle of the screen, you see the capsule-shaped crew module, which is a simplified version of the Orion crew module. It has the same weight, same shape, and it still responds with the same millisecond precision relative to the commands that we send. That was built in-house at NASA, a combination of activities between Langley Research Center, Johnson Space Center, and Armstrong Flight Research Center. Underneath that is the separation ring. Now that's a 3.5-foot tall ring that basically mimics the top of the service module, and that provides us the separation interface. On the left-hand side, you see the partially assembled launch abort system. So you see the tower up at the top, and you see how it covers the crew module. And so those panels are called ogives, and you see a couple of them in place, but that way you can see what it looks like underneath. So it protects the crew module during an abort. So then on the launch abort system was provided by Lockheed Martin, and that's actually one of the major items under test that we are testing. And that's a production article, and that's the same design that will be used for Artemis 2. And then on the right-hand side, you see the full stack. Underneath the launch abort system, you see the booster. The booster is provided by the Air Force and by Northrop Grumman.
All right, very good. And you also have an animation that kind of walks us through all the major steps in this test.
We do.
Talk about that as we roll that animation for you.
All right, so if we go to the video, here we are on the launch stand at Slick 46 at Cape Canaveral. And the booster is going to give us about 500,000 pounds of thrust at liftoff. In order to get us up to the right test condition at 31,000 feet, we actually had to add over 100,000 pounds of ballast to it just to slow it down because it's pretty sporty. It uses a Peacekeeper first stage solid rocket motor. So we've got about 55 seconds in ascent. When we get up to about 31,000 feet, we've got tremendous aerodynamic pressure on the vehicle. And we get a signal from the booster. We've reached the condition. And it tells our flight computers and our flight software to initiate the abort. At that time, we actually ignite the abort motor, which is about 400,000 pounds of thrust, pulls about 7 Gs. Also ignites the attitude control motor that provides the steering that you see. It rotates the vehicle around, reorients it, and so it puts the heat shield forward for descent. And after 27 seconds after the abort, the third motor lights. This is the jettison motor, and the jettison motor pulls the launch abort system away from the crew module. After the jettison motor goes, the crew module is in free fall and descends back to the water. All 3 items will impact in the water. You just saw ejectable data recorders come out. The ejectable data recorders actually are a backup to our communication system, so they carry the data for the whole flight and eject into the water in pairs. What you didn't see is parachutes, and that's because for this particular flight test, that's not one of our primary objectives. They've already been tested really thoroughly, so we're not using parachutes for this test. There's really 2 main objectives for what we're trying to do. One is to execute the abort itself and demonstrate that we can do it end-to-end, but the second is data. We have almost 900 sensors, different instruments. We have temperature sensors, pressure sensors, microphones all over the vehicle, and so we get that data back from this flight test, so that's another major objective for us.
And we have this graphic up now that we can show what people would see if they were in Cocoa Beach looking northward towards the launch pad.
Yeah, absolutely. So we were real excited about this to get this out there for folks to see. So this is looking north, and you can see the 1, 2, 3, 4 show where the major events will occur along that parabola. You can see the highest altitude we get up to on this is somewhere around 44,000 feet, 45,000 feet, and impact in the water. And this shows the landing trajectories for the launch abort system and for the crew module for our reference trajectory. So hopefully folks can come out and take a look.
All right, very good. And Jenny mentioned no parachutes, Mark. So this is part of a effort to hurry up this deadline, accelerate the deadline. Talk about that and the overall program of Orion.
Yeah, sure. Thanks, Daryl. And good morning. Welcome. Thanks for coming to our flight test. Orion has always had a really exciting and challenging mission. We're going to take people farther into space than we've ever gone before. And it was just this March, about 3 months ago, our mission became even more exciting. Vice President Pence announced this administration's goal, as Daryl said earlier, of landing the first woman and the next man on the moon, on the surface of the moon, by 2024. And our program, Orion, has a really key role. We'll be taking the people from the Earth to the gateway where they'll get into the lander and return to the moon. So we were extremely excited about the announcement. You might imagine we have a very focused team. It elevated our focus. And right now, as we speak, we have the hardware, the crew module and the service module for all of the Artemis missions that are needed to get the crew to the surface of the Earth by 2024. We have all of them in various stages of manufacturing and testing. So, for example, here at the Kennedy Space Center, just a couple miles south of here in the Armstrong Operations and Checkout Building, we're finishing up work on the Artemis 1 crew module and service module. And if we could have the pictures, please. This is the Artemis 1 crew module. Again, just over the weekend, we actually weighed and measured its CG, a detailed procedure, so we understand the mass properties very well. And the next slide is the Artemis 1 service module, and this is about a week or two old. We were doing an acoustics test to make sure we understand how the service module will respond during the noise provided by Ascent. So these articles are both in the Operations and Checkout Building. We also, in the ONC building, have the Artemis 2 crew module, and in a similar factory in Bremen, Germany, our ESA and Airbus colleagues are very busy, well into manufacturing of the Artemis 2 service module. So those articles are coming together, and we are well into initiating the long lead procurement for the parts we need for the Artemis 3 vehicle. So we are really excited about this mission, and Orion is on track to support the administration's challenge. And that brings us to today and tomorrow's test. This test is extremely important, as Daryl mentioned earlier. In Orion, crew safety and spacecraft reliability are very high priorities for us, and our launch abort system is a key safety feature of the spacecraft. It will protect people like Randy, the crew members who fly on board Orion. It will protect them during the most challenging part of the mission, which is the ascent phase. And this will be our second test of the abort system. The first was from a pad, from a standstill. This one is actually more challenging. As Jenny described, we will intentionally initiate the abort in flight, about 55 seconds into flight. And at that time, the combined vehicle will be going over 800 miles per hour, still in the atmosphere. We're at about 31,000 feet. So there's a tremendous aerodynamic forces on the vehicle. And that's how we pick the test points for this, the most challenging part of the ascent that Orion will ever see. So we want to demonstrate that the LAST works in this environment. In terms of the vehicle itself, the vehicle physically is beautiful. I have a hard time telling the difference between the pictures and the real vehicle in these animations. It is really beautiful. On paper, we had our launch readiness review on Friday. We met with the range this morning. Everything is very clean. And the weather for tomorrow looks really good. I've been told the weather today and tomorrow and Wednesday is as good as it gets in this part of Florida during the month of July. So things are really looking good for the test tomorrow.
Great, 80% go, as I understand it from the weather officer. Randy, let's move to you and talk to me about the human element of this test. You hope to never have to go through this, but if you do, it's comforting to know it's there.
It's certainly a very exciting test for us tomorrow, and because it is so important, because it's the only one of its type in the dynamic flight environment. the environment where it's going to be needed most. And so you heard Jenny and Mark talk about the, being the maximum dynamic pressure. Well, think of like a boat going through the water, and the engines power up, and you get that wake. Well, then you get the top speed, and the engines are going at full speed. Now there's the big wake, and there's spray going everywhere. Well, that's the rocket's trying to push through the air molecules in the upper atmosphere, and we're reaching the point where that's the most pressure on the bow of the ship, and we're going to then fire the rocket to pull it away. Why is this hugely important? Because we got the world's largest, most powerful rocket in the SLS being built that's going to carry the Artemis missions into space and beyond low Earth orbit. Well, if you got the most powerful rocket pushing the engine of the boat, up through the atmosphere, well, you got even more powerful launch abort system to be able to pull the crew away from it if there's a problem with that rocket. And so we've got the fastest accelerating launch abort system ever designed. We've then got, in this attitude control mode, only controllable, human-rated, attitude solid rocket motor that exists. So this is the first time we're doing that. So that's a neat, feature. And all this is to be able to keep the crew safe if there's a problem. And so we are looking forward to seeing the results of the test. The neat part is the next time this full launch abort system flies, there'll be crew underneath it in Artemis 2. And so that's why it's really great to be able to see this test. The weather's looking good. The vehicle's been prepared. The team is ready. And we're looking forward to a great day tomorrow to prove and show that this system works. So we can say that we've got a launch abort system. We've got a parachute system that are all ready to go for the first humans in the vehicle.
All right, thank you, Randy. And now we're going to turn it over to questions from the media. Remember to raise your hand and then wait for the microphone, which are on both sides of the room, to come to you. State your name and affiliation, and then your question. And we'll start in the third row with the gentleman in the middle there.
Stephen Young with Spaceflight Now. For Randy, could you just maybe discuss a little bit about what a crew member would feel in this kind of a maneuver? What sort of G-forces? It seems like that flip around would be quite a ride.
Yeah, certainly the 7 Gs is what's going to get your attention the quickest because it happens very quickly, but it's a short duration. The good news is it's not like an airplane where or a fighter plane where you're pulling the Gs and the Gs are going this way in the Z direction and basically pulling the blood out of your head. It's basically through the chest and pulling you away. So we've trained in centrifuges for that for space flights. We also on reentry. Even in the the Soyuz capsule, we got to above 5.5 Gs. So it's not an unusual type of thing. It's just but the speed at which it happens, and it's also typically it's going to be automated. And so we sensors let us know that we need to have it aboard, and the system goes. So it's not like the crew's always pushing the button and they know exactly when it's going to happen. So you have to kind of be prepared at any point for it. But after that initial pull away, once those G forces come off and the maneuver starts happening around, the good news is we haven't been up in space for 5-6 months, and we're trying to get our neurovestibular back together. We've been on Earth. We just left Earth, minutes before, and so it's going to feel like swinging out of a pendulum, kind of like those rides at the amusement park where it sits there and swings back and forth. You'll kind of have that swinging motion until it gets to the right attitude to orient the capsule for the jettison motors to fire, and the capsule will be in the right attitude for reentry. So once that swing around happens, it should be a pretty benign ride on the parachutes back down to the ground.
And physically, you got to be ready for those forces to exert on you, right? And actually do some maneuvers to physically be ready.
We say an elephant standing on your chest is what it is, and I think for the abort modes, it might be like 1.5 or 2 elephants.
Wow. All right. Next question. We'll go to the front here, on the front left. Ken.
Hi, Ken Kramer, Rocket STEM Space Up Close. For Randy and for all of you, a few months ago, your colleague Nick Hague went through a real abort with the Soyuz. I'm wondering, were there any lessons learned from that you applied to this? Anything you changed?
Okay. The lessons learned, that I got from Nick, was certainly that we have to prepare for this, even though it's, a low likelihood of happening. I mean, it had been 35 years since anyone on the planet had to exercise their launch abort system. Fortunately, we go through all the training for the Soyuz, and we're ready for it. We brief with the SAR recovery forces. We brief with all the launch folks. And our Russian colleagues did a phenomenal job. It is as if they had expected it at every launch that they've had the past 35 years, and this just happened to be the time that it actually happened. And so the motor and everything performed the way it's supposed to. The sensors, let the Soyuz vehicle know that it was time to, execute the abort. And then once they were, the abort had executed, the crew was, being monitored. They were being communications even before they touched down. And the SAR forces were right there as if they had rehearsed it just the day before. And so that was definitely a good message to all of us that, hey, this is serious stuff. This isn't just okay, it probably won't happen. We need to be ready because it has ultimate consequences if it doesn't. So that's why Jenny and her team getting this thing ready and proving it tomorrow, is huge for us to be able to have that confidence that the whole system we've designed, works. And certainly the lessons are not so much in exactly their design informing our design, but just the fact that the operations and the mindset needs to be that this could happen and we need to be ready.
All right, next question. Standing up there on the left.
Hi, Bill Harwood, CBS. You mentioned the Soyuz abort system. Of course, they only use their rocket for part of the abort regime. They can use springs higher up and smaller thrusters and that sort of thing. Can you kind of describe the operation of the LAS from the pad? When does it become ineffective, or when do you not need that anymore during powered flight? And a really quick follow for Jenny: how many of those data recorders do you need to recover in terms of mission success, or can you get by with not recovering any of them? Thanks.
Take the recorder question,
Sure.
and then I'll address the...
Okay, sure. Yeah, I'll take the data recorder question first. So we have 12 total, and they eject in pairs starting 20 seconds after jettison all the way down to the water every 10 seconds. That is a backup system relative to our RF comm. And so for our S-band communications, we actually downlink all the data during the flight. And then after last jettison, we actually start a rebroadcast of the data from 3 seconds prior to abort. And so we'll get a couple more rebroadcasts of that critical data on the way down. So our communication system end to end will get us all the data that we need. The data recorders are really a backup system, but from a how many do you need, one data recorder with the data on it would provide that full backup capability for us.
They're very thorough, 11 backups.
And your question on the abort architecture, Orion is similar in many ways in that we have a series of aborts during the ascent phase. And the first, what we call launch abort system-based aborts are mode 1 aborts. And they're applicable from when the crew ingresses the vehicle until several minutes into the ascent after we separate the boosters. After that point, we jettison the LAS. We shed the mass, gives us more performance to orbit. And we don't, if we had to abort any time after that, before we get into orbit, we would use our main engine supplemented by our aux engines, our liquid engines, to abort to orbit in that case.
What time or altitude is it?
Yeah, it's several minutes. It's a little over 2 minutes into flight, and the altitude I don't recall. I will get that for you.
All right, very good. Next question. Second row in the middle here with his hand up.
Jeff Faust, Space News. Just curious what differences there are in the LAS between the one that's going to be tested tomorrow and the one that was used in the pad abort test several years ago.
Yeah, very little differences. In fact, the intent is this is the production LAS. We did, when we flew the pad abort test several years ago, we did note several items that we wanted to improve upon. For example, we actually made the abort motor smaller. We didn't need quite the thrust. We changed the jettison motor installation materials, and we improved the attitude control motor. So all of those changes have been incorporated into this Ascent Abort 2 motor, and it is intended to be the production version.
All right, very good. Let's go over to the other side of the room in the back. The gentleman with his hand up.
Hi, Emery Kelly with Florida Today. Can I get a bit more on the level of automation we're talking about? You know, how much human control can you inject into this? You know, at some point, can you say, nope, we're taking over? Or is this, would it happen so quickly that computers have to do all the work? Thanks.
Yeah, certainly the vehicle has a lot of sensors. The SLS, the ultimate production system. SLS has sensors to let Orion and communicate to Orion if there's an issue. Orion has sensors that can trigger the abort as well. The human part is the crew will have a button, an abort button, that if they sense something out of control and the automated system has not already kicked off the abort, the crew can actually hit the abort button. Once it's flying, that's all automated. It's programmed. The LAS flies itself, and we look forward to seeing that work tomorrow.
All right, very good. Gentleman in the third row here on the left side. Wait for the microphone to come to you.
Hi, Robert Perlman with Collect Space. Given that we're just about 2 weeks away from the 50th anniversary of Apollo, I wonder if Jenny or Mark, if you can talk about how this test compares to the Little Joe tests with Apollo and before that even Mercury capsules, and how the hardware differs from what was used on Apollo.
Go ahead.
Okay, sure. Well, they're very similar to the Little Joe test. The purpose is the same, to launch the spacecraft and then demonstrate the abort capability. Our launch abort system is improved over the Apollo. It's a similar architecture. We call it a puller, in that the launch abort system pulls the spacecraft away as opposed to pushing it away. But past that, the biggest change from the Apollo is the attitude control motor that both, I believe, Jenny and Randy mentioned. Apollo did not have an attitude control motor. There was a very simple pitch motor, so it pitched the launch abort system over, and if it was the direction you wanted to go, great. But if you have any, you might imagine some of the circumstances that could trigger an abort could actually put different sorts of rates on the vehicle. This launch abort system has this attitude control motor which will stabilize the rates and fly in the desired direction. So it's a really big improvement over the Apollo system. And we talk about the abort envelope, and that's the abort conditions that you can successfully abort from, and our envelope is expanded from the Apollo envelope because of this abort motor, because of this attitude control motor.
Okay, very good. Let's take some questions now from social media. We have them coming in on the hashtag #AskNASA.
So we have two social media questions to start. Since there are no parachutes on the capsule, what do you expect to happen to the capsule when it hits the ocean? And are there any experiments inside?
So we don't have any experiments inside, but we do expect during free fall, the capsule is likely to tumble. We don't have any attitude control system on it at that point, so it's likely to tumble. It's going to hit the water at about 300 miles an hour, so we are not expecting it to stay intact when it hits.
And it's weighted down to sink, right? Once it
Yes,
makes
we are
impact.
absolutely expecting it to sink.
All right.
As
Very
Jenny
good.
mentioned, we did that intentionally. We removed the parachutes, the attitude control motor, the attitude control system, the RCS thrusters, in order to perform this test as early as possible because we want to get the data. We want to inform the missions going forward.
All right, let's go back over to the right side of the room. The gentleman in the back.
Jeff Kluger, Time Magazine. Just a very fundamental question. Can you give me the height of the entire stack and the height of each of the components?
The stack is about 93 feet, and the abort test booster, the rocket piece, Phil, if I'm off, please correct me, it's about 40 feet, and then the Orion flight test article, including our SEP ring, the crew module, and the LAS, is about 53 feet. 40 and 53, 93 total.
It doesn't look very tall on the pad until you get close to it, and then it looks big. It's huge. All right, next question. Do you have any more questions in the room? All right, any more from actually the gentleman 3 rows back?
Stephen Young with Spaceflight Now. For Jenny, are any of these recorders likely to turn up on the beach, and do they have a note if anyone finds them?
They do, in fact. They're labeled. They are in fact labeled. So this is what the data recorders look like. This is one of the canisters from which they eject out of the crew module after last jettison. And so this is what they look like, a nice bright orange. They float, and they do have a label on them. They also actually have a beacon and a transmitter so that we can locate them. So when we go out to find them, we actually will be able to get their tracking information and go locate them and pick them up. But yeah, they are in fact labeled.
And we did practice, so we proved we could find them and recover them. But if you see anything like this tomorrow, let us know.
And I believe it has an email address and telephone number on it, doesn't it?
It does, in
Contact
fact.
information?
It does.
Yeah,
Yeah.
very good. So
Yeah.
it's all there if you happen to find it. Bill, another question?
Yeah, just one more quick one. What's the range offshore for impact? How many miles offshore? And is it you're launching due east, or is there some inclination to this? Thanks.
Call Jenny.
It's east, and the reference trajectory that we showed you earlier shows the crew module about 7.5 miles. The booster goes outside of that a couple more miles, and then the launch abort system is just inside of that. So that's kind of that whole box out there, that range.
All right, a question in the back of the room on the left side. Ma'am?
Yeah, Claire Riley from CNET. I just wanted you to talk through, after this test, which is obviously quite critical, your next major milestones that, if everything goes well, you're hoping to achieve by 2024.
Sure. I talked a little bit about the work we have ongoing in the operations and checkout building with our Artemis 1 vehicles. The next big milestone there, which will happen sometime towards the end of July, is we're going to mate the crew module to the service module. So we'll have one integrated stack, and we'll do a series of tests to that vehicle to make sure the crew module and the service module function well together. And when that series of testing is complete in the fall, sometime in September, we put that stack on an airplane and fly it to Sandusky, Ohio, where we have a environmental test chamber. We'll put the integrated spacecraft through a very rigorous thermal vacuum test and some EMI, EMC, electromagnetic compatibility tests.
All right. Any more questions for our guests? All right. Well, given that, we're going to wrap it up. I want to thank you, Jenny, Mark, Randy, for joining us and sharing your knowledge with us. We're excited. Hope the test goes well. A programming note for NASA TV. Our coverage will start at 6:40 in the morning on July 2nd. The launch, the pre-flight test, is scheduled, the flight test, I should say, is scheduled for 7 in the morning Eastern Daylight Time. Then, 2 hours after the test is completed, we will hold a briefing to tell you some of the preliminary results. That's going to do it for us for today. For NASA Television and everyone at the Kennedy Space Center, I'm Daryl Nail. Keep looking up.